Hello everyone. Let us start. Let us wait for a few more people to join, then we can start.
Good afternoon, sir.
Hi, good afternoon. So, welcome to week 4 of these interactive sessions. So, this week the lectures that covered different gradient descent type of algorithms. So, you saw how gradient descent works, why we need techniques such as momentum or algorithms such as nested or accelerated gradients. We also saw stochastic and mini-batch gradient descent, and also some techniques such as adapting the learning rate based on the point in the algorithm or point in the iteration where you are at. So yeah, so we can discuss whatever doubts you have regarding these topics or any topics from the previous courses, previous lectures, or if there are any doubts from previous assignments, we can also discuss this. Yes.
I have quite a few doubts now.
Yeah, yes, yeah.
I'll start with uh, we had this bias correction
Mm-hmm.
derivation.
Yes.
Uh, it is like just one time if you understand why is that needed,
Mm.
afterwards you don't need to remember and go back. No, generally I understood, okay, that is how it is required, but then it was a very detailed derivation. So I was wondering, like for us, we don't do we need to
Oh,
remember that
so
derivation, you know?
no, no. So whenever you're using Adam, this, yeah, it's good to understand it, but you don't need to remember it because
Yeah.
if you're using libraries, these things are already implemented in those libraries. So
Mm-hmm.
it's okay. You have to understand it.
Even if it
That's
is
needed.
even if that library is not there, if we just know that, okay, this is the bias which we need to, bias correction, this is what we need to do. Beyond that,
Yes. Mm.
we don't need to. And
Uh,
these optimizer formulas and all, do we need to remember?
so you don't need to
Some
remember
are like
because
really big ones. By the time you
ha
reach
ha ha.
Adam, it becomes really big.
Yeah, yeah, that is true. So most of them are like variations of gradient descent. So that is the
Yeah.
golden algorithm that you have.
Mm,
And then after that, you just need to know what are the terms like how do we use this look ahead momentum or this look ahead gradients. You just need to remember those like what are the techniques of the defined optimizers. Don't need to
mm,
remember specifically these no
big
these
formulas.
terms. Yeah, yeah, yeah. You don't need that. Just need to know physically what it means that you're using this algorithm or this algorithm.
Okay. A question regarding if we want to check all these techniques, optimization techniques,
Mhm.
and do we need a neural network only, or with a single neuron only we can test?
So actually, you can even without any neural network, you can do that. You can give.
Yeah.
So these are not neural network or deep learning
Yeah, these are
specific
not, because
algorithms,
this is to do with optimization, so
right?
we can do it. But
Huh.
I faced a problem. Yeah,
Hmm.
last week I had done this gradient vanilla gradient descent, the
Yes.
code provided in the lecture,
Hmm.
simple one. And the when I changed the inputs,
Hmm.
then uh, it is not working. In the sense, I'm getting very big error, loss and all.
Okay.
I
Hmm.
mean, my initially my numbers were such. When I reduced the number to point one point, so two things I noticed. So when I faced this first issue was like when I got this error as 196. And I was like,
Hmm.
what is this? How can that
Hmm.
be?
Huh.
There's something wrong in that. Then before doing anything, I just went and did in Copilot. I just checked. So he said, "Oh, you need to normalize your." So that was a good learning. I had
Right.
studied the normalization, so I
Hmm.
understood the practical live example. I got that okay,
Hmm.
we need to normalize, but
Yes.
after normalizing also,
Hmm.
so I kept it in a range only, a small range only. I kept my inputs, two or three inputs, but I kept it in a small range. But in spite of that, if I'm taking in that simple vanilla gradient descent, if I'm taking that point one, point two as input, then it is
Hmm.
working, getting
Hmm.
0.00 some error. And if I'm taking slightly the more I increase the numerical magnitude
Hmm.
of that number,
Initial
uh,
points. Okay.
yeah, the x value only, inputs only, not
Okay.
initial. X,
Okay.
x points only. The moment I increase it, and
Hmm.
gradually, my error. So, what is the logic? I did not understand.
Okay. So were the errors decreasing at all, even when you're using larger
Error
information?
was error decreased, but then the error became like when initially it was point 0.2, then 0.00. Then when I
Hmm.
made it as 1 point something as my input, then the
Mm-hmm.
error became 0.8, and then I increase it further and even. And if I have I kept my input and output x and y as like as a square function kind of
Mm-hmm.
a parabolic function I
Right.
kept. So x square plus 1, I just randomly, I just wanted to see how things work. So I
Mm-hmm.
just kept x square plus 1, just two inputs I took,
Mm-hmm.
and my error just shot up. Now it is not like be below I think point 0.3 or something, and then uh, erratic it was like my as I'm increasing the learning rate, it became till 300. I had to, like, I just wanted to see what it is in that same code. Now the
Oh, so you
moment I put,
increased. Huh.
yeah, the moment I don't know what was happening. I did two things. So one is
Mm-hmm.
like after normalizing also, if
Mm-hmm.
I don't normalize, the error was like 3000 or something in my parabolic. Then I
Oh.
understood, okay, my inputs have to be smaller. But
Mm-hmm.
why my inputs have to be smaller?
Mm-hmm.
Everywhere in all examples, wherever I have done these courses, and they
Mm-hmm.
used to take point 0.1 like that, small values, and I was like,
Mm-hmm.
okay, never mind, they're taking some value point. But
Mm-hmm.
why is what is I don't know. I would like to know why, or
Okay,
what kind of
so
inputs is what I should be taking. I understood it is to do with inputs.
so in general, uh, the convergence of these algorithms does not depend on your inputs because the ultimate goal is to get a loss of zero. It
Yes,
does not
but
depend
that is
what.
not happening. Yeah.
Uh, but for this case, maybe yeah. So what are the ranges of learning rate you are using?
Initially and all for this point 1, point 2, 3, 3.5 was working. The
Oh, learning
moment I
rate.
increase, yeah,
Oh, actually, that is a
if,
large, very large learning
yeah,
rate.
and if I bring
Uh,
it down, then it was not working.
Oh.
3.6 to be precise in that example, which was same example that was given
Mm-hmm.
uh, in class.
Oh.
I didn't change anything at all. That was the,
Mm-hmm.
and then the more increase as I'm increasing, so it is definitely not okay, but this is the pattern that I noticed.
So, and the thing is, okay, how are you initializing the weights?
I just gave the weights manually only,
So, okay.
minus
Uh,
one, or in that
mhm,
example it was -2, -2. I
mhm.
continued with that only.
Acha. And did you try and print the weights after, say, some epochs of training? So,
Sorry,
so
did I?
after, so suppose you started your initialize your weights, say minus two, something like that,
Mm, mm,
and you ran your gradient descent for say 10 iterations.
mm.
And did you go and print the, did you see what are the new weights that you
Yeah,
get?
in that example, it was I print. I mean, I put everything. I kept appending it in a list, and
Mm-hmm.
I got a nice list. And towards the end, it was increasing. So I understood, like, okay, so in between was like 3.6 was the
Mm-hmm.
learning rate in which it was working, in which it was minimum. I mean, I didn't try to plot it and all, because for plotting again it said
Uh-huh.
you need an array and you need this and you know that. I was like getting deviated from what I wanted only.
Acha.
uh, so I did try to plot something, because I
Mm-hmm.
also wanted that same error surface which we were learning, everything we were learning on that error surface. So I was like,
Mm-hmm.
okay, in mine also I want to see the error surface. So I was not, past 2 days I've been doing that, and I don't know why. Uh, Inputs should be small.
So,
That is
uh-huh.
the conclusion, my
Uh,
conclusion.
so
But
your
why?
function was, yeah, your function was x square, y equal to
No,
x. What was the,
with that,
what was,
no, no, no x square also with the linear thing also. I just double 2x I did. 2x plus
Okay.
1. For that also, if my x is big, that was not working.
Hmm. Hmm. And your function was the sigmoid function itself, right?
Yes, sigmoid function. So I was like, then I did a copilot on that also. Can sigmoid take parabolic inputs? Yes, sigmoid can
Yes,
take
it can.
parabolic inputs.
Hmm.
So I thought like maybe that is not okay. But if I give that same, like right now, I
Hmm.
have x as 1,
Hmm.
y as 1.3. That's all I've given.
Okay.
X as 1 comma 3 and y as 1.3, 2.3.
Hmm.
And if I run it, my error I'm getting, I mean, I have not final error only, I'm just printing
Hmm. So, okay.
0.8 and all. So, or
So
what
maybe,
should ideally people what do engineers use for input? Like if
so,
I want to test now
uh, so
random.
actually in the sigmoid function that they're using, it has certain problems like your if your x is very large or your function
Hmm.
is very large, your gradient becomes almost one, right? Because
Yeah.
if you look at the curve of the sigmoid, if you go
Yeah.
too much to the right or too much to the left, it becomes very
Uh,
large. So when you
uh,
are using x square plus 1 say inside the sigmoid and your
uh,
x is large, your function gradient itself becomes almost 1. So you don't
hmm.
see much changes in that case.
Hmm.
Are you able to understand that?
Yeah, I can
So
understand that.
probably that could be the issue because
Okay.
you have 1 by 1 plus exp of x square plus 1 and you put
So
x
then,
5. Uh,
then it is subject to specific
instead
functions.
of yeah, instead of sigmoid you can try. Okay, so I'm not sharing my screen till now. Okay, so instead of sigmoid you can just work with, let us say you take say sine x to be an example.
Okay.
And so yeah, for so sin x, you know the derivative, you have to manually code it cos
Yeah.
x, cos of that much.
Uh,
Then maybe you will then you can try that out. I think you won't face this
okay.
issue.
I'll try that.
Hmm. I think
But
that is a problem. Hmm.
mm,
Because
okay.
that is the specific change that you are having.
Yeah, yeah. But
Mhm.
good that I encountered uh,
Yeah, yeah, it's nice.
like that. I got stuck there only.
Mhm.
And yeah.
But it's good to look at these problems because now you
Yeah,
know
yeah.
how the
So you
sigmoid
will
behaves.
correct, correct.
Mhm.
And also this normalizing thing also.
Yes.
Okay. And yeah, another one was uh, week week 3, previous
Hmm.
weeks,
Ah,
question number 2.
let
Uh,
me
week
question
2,
number two.
question number 2. Week, sorry, week, not week 2, week 3.
Ah,
Week
three.
3 assignment, week 3 quiz, question
Hmm.
number 2. I'll also open 1 minute. Yeah.
So
Suppose
if
all elements in the input vector are 0 and
hmm,
corresponding true label is also 0. If the weights are also initialized to 0, what is the loss value with cross entropy? With cross entropy, we are using loss as mm, P log,
so
I mean P of
why log, yeah, y log y.
Yeah, y
So
log, sorry,
y
y
log.
log
Mm,
y, and that
yes.
y is true,
So
true value.
y log y hat. So basically.
Yeah, but yeah, y log y hat. So
Mm-hmm.
my everything is
So,
zero. So y is
okay. So if it's not about it's less than 0.
the moment y is my true label. So I'm multiplying with a zero, then it'll anything will be a zero only. So that because the explanation is not given.
No, no. The y will be, so it is summation y will be 1,
Hmm.
because that is where is your loss non-zero. It's a one hot type of thing, right? So something like this. That means,
Okay, okay, wait, a screen, let me see. You've shared the screen?
yeah, I'm sharing my screen. Yeah, hold on. Yeah, are you able to see my
Yeah, yeah,
screen?
can see. Yes.
So your cross entropy loss is basically yc log y hat. Let's see,
Yeah.
right? And this is
Mm.
your true label. So
Mm.
it is 1. So this is basically 1 if say c, how do I say it? So it is
Or
something like
that particular.
Mhm.
Uh, okay, okay,
So
I got it. For one, it'll since it's a one hot, one of
yes,
that
yes.
will be one.
Uh-huh. So yc log y hat. So this is either yc is either 1 or
Okay, okay,
0,
okay.
and you're taking a log of the remaining terms.
Oh yeah, that
Hmm.
one hot is what I did not because I considered
Yes.
all of them as zero.
Mm-hmm.
Okay, 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 got understood then. Thank you.
Okay.
Okay, I'm done with my doubts.
Okay. So others, anything regarding this week, regarding a different algorithms or anything from previous uh, topics?
Hello.
Hello, hi.
Yeah, hi. So there was the first question related to the bias correction, right? Where we are doing the bias correction for the weight. And there is
Yes.
an assumption there, right? That the expectation of, like if I go to the equation, right? That the
Uh,
expectation should be equal. That the
yes.
expectation of the momentum should be equal to the expectation of the change in the weight.
Hmm.
So why is that assumption taken, right? I did not get that.
Okay. Okay. Let me.
I think it's on slide number 88.
Mm-hmm.
I remember a professor drawing and showing some like it was basically a distribution curve, but I did not get why is that assumption taken.
Yes. Okay. So this MT that you are taking, it's like a running average, right? So you get some. So your MT is written something like this. Thanks. So this is your MT, right? So this MT is basically you're taking this thing. Uh, you are taking all of the previous uh, gradients and then momentums, and you're taking a average of this. So because of that, uh, you are taking this over a stochastic, I mean, many number of points. So you take one point, calculate your momentum, you take another point, calculate your momentum, and on an average you want to say that you want to estimate the actual momentum or actual gradient of the curve. So because this empty that you're doing taking, it depends on which point you are taking, right? So suppose you take a point x1 and you create some empty for this, or you compute some empty for this. You take some point x2, you compute some empty on this. So because it is you're choosing these points x1 x2 probabilistically, you want that on average your empty should be equal to the gradient of the this expected gradient that you have. Because you're taking all of these things, all of these points probabilistically, on average you want that whatever estimate that you get of the momentums should be equal to this thing, the expected gradient. So is that what you're asking?
Yeah, yeah,
Yeah, hopefully that is clear.
yeah. I'm trying to understand. Yeah,
Okay.
like it's a bit clear. Yeah, but I think yeah, I'll go through this again.
Yeah, you can ask. Yeah, okay.
It seems a bit complicated, but I'll try to understand it again.
Okay, so think of it like this. I'm giving a simple example. Suppose I give you a coin which has, say, probability of heads is p and probability of tails is 1 minus p. It is not 50-50, just some probability p. And I ask you what is the probability of head. So what will you do? You will you toss the coin, say, hundred times, and you observe what is the number of heads and number
Yes.
of tails.
Yeah.
And then instead of p, you will get some estimate. Say number of times your heads occur is, say, 30, and number of times your tails occur is, say, 70. So
Okay.
you will say that this p is probably something like 0.3. You're not correct, but you may not be correct, but you say that because you have observed it 100 times, you
There
want
is some
to
bias in the coin.
there will be
Like,
some bias.
yeah,
Huh.
yeah.
So that means the expectation of this p hat that you calculate, you wanted on average, this should be equal to the exact p that you are getting. So why we're taking this expectation is because we are doing an experiment multiple times. So same thing goes here also. You are sampling a point, multiple points, and you say that on an average we want the momentum of our points to be equal to the expected gradient of the, because we don't know the true gradient,
Okay.
because it is stochastic in nature. So say for one point you get a gradient of, say, 0.5. For a second point you say get a gradient of 0.7. You don't know what is the exact gradient, but on average you want to approximate that gradient, and that is what we want to do here.
Okay. 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 Yeah, I get it now. Yeah. Thank you. Thank you so much.
Okay.
And I had one more question. Okay,
Yeah.
like it was related to the way the weights in gradient descent, right? We
uh,
update the weight by subtracting a step function with respect to the change in the step, change in W. Okay,
yes.
and like when I went through these algorithms earlier, we were
Hmm.
like I basically read it that the negative sign we are subtracting it because we want to go in the direction of descent.
Negative gradient, yes.
Yeah, negative. But here in this slides, right, it is explained using Taylor series, right?
Yes.
Yeah, I was not able to understand how did they come to the negative sign using Taylor series there.
Okay, let me go to the site, we'll derive it. Hold on. Okay. So, okay. So Taylor series basically says that if you have some function value at a point, so suppose I take some function like this, and I take a point like this. So suppose this is my point. What is the function around this point? So here it looks something like this. Or if I take a point here, the function looks something like this, right? And you want to approximate the type of function that we have. Say here I can just say that this function is a line, but here I can say my function is like a inverted type of parabola and so on. And so Taylor series tells us Taylor's if we take the Taylor series at a point, we want to see how can we approximate the function at that point, because we don't know what is this function, we do not know that, but at certain points can we approximate it. So we use that to compute the approximation of the loss static, because now the function that we are interested in is a loss function, and we're interested in reducing this loss function, or we are going to a minimum of this loss function. So suppose I am at a point theta, and theta is my current set of parameters that I have. Theta, or you can say W. Let us say theta to take the notation. And so if I want to check the function, so L is my function. So I want to check the function value at a certain distance from theta. So let us say this is my function. This is my theta axis, and suppose this is the point I'm at theta, and I want to say what is the value of the function at a distance of eta times u. So let me say that this distance is eta times u, and what is the function value at that. So tail, because now we say that eta is small, we are at a very close neighborhood of this theta. We're in the neighborhood of this theta parameter. So the function value can be written something like this. What is the function value at theta plus eta times u transpose, and some other terms are there. So if eta is small, say eta is say 0.01, eta square becomes 0.0001, which is small, and we can ignore the remaining parts because those are anyway small values. So let us just concentrate on the first two values because they are somewhat okay. So now what is the goal of gradient descent? We are doing gradient descent, so we are at some point in the function, and I wanted the next parameter that I get that should have a lesser loss than this. So if my loss is something say 100 here, I want my loss to be smaller, in this case say 50 something. So that means if I take this, so initially my function value was, or now my function value is this one, because I have moved by gradient descent, and before this my function value was this thing. Now because my new function value should be smaller than the small function previous function value, so this difference should be less than 0, right? Because you're decreasing the loss.
Yes.
And now, yeah, so now if you put this here, we get that this is nothing but eta times u transpose grade of L theta should be less than 0. I'm just substituting this thing here because this L theta will cancel each other out, and then you get this. And also eta is a known quantity because eta is your learning rate. We don't need that. So that is anyway positive. So we are left with this quantity. This should be less than 0. So now we want to say what is the, so now do we have a vector u. So that vector u is the direction that we want to go, and the gradient of this is the direction that we have. So it's something like this. We are at theta, and I want to go to a different. So we are at theta, and I want to go to a new vector theta, something like that. So I am drawing it in 1D here. This was a 1D representation, but in multiple dimension, these thetas are like vectors. So now I am at some theta, and this is my theta plus n u. So that means I am moving from theta to a direction u and adding these two together to get the uh, new set of parameters. So is this diagram clear? I am at a vector theta and I want to move in a new direction u. So this is my new direction. Yeah, this is my new direction. So my next set of parameters will be the sum of this and this. So that is what we get here, right?
Yeah.
Theta, and I want to go to theta plus eta u.
Okay.
So is this clear?
Yeah, yeah, yeah. I got
Yeah, okay. So now what we want is that this new direction and the old gradient must be zero. Sorry, must be less than zero. That is the dot product should be less than zero. So we can, because it should be less than zero, we can say that we have some vector here, say gradient of L theta. We have another vector, say u, and we want so dot product is basically cosine, and we want the cosine to be less than zero.
Okay.
But we know that the cosine of these two vectors, so if I say that these two have some, let us say, beta angle between them, so by formula of cosine we have that this thing,
Yeah, it should be between 180 to 90, right? To get
yeah, this should be between, so cos should be between -1 and 1,
okay.
right? Some gradient of this. And then they do some multiplication and say that okay, we want that uh, this to be negative. So I think they do that something here. So they just say that this is k, and you have cos k times cos beta should be between minus k and k, because earlier it was between -1 and 1. Excuse me. And now if I just multiply k on both sides, we want this to be between minus k and k, right? And now we want that we want this to be negative. So when is it most negative? When this beta is -1. So we have, say, gradient of L theta in this direction, and the new direction is in exactly opposite direction. uh, this is u. So this is where the concept of gradient descent comes in. So I am diverting a bit. Let us say we have this graph here, and at this point my gradient of the point is in this direction, right? Because that is how gradient is designed. But now my minima is in this direction, so that means, so this thing says that yeah, this thing that uh, beta should be 180 degrees. It says that if this is my grade of L theta, now I should move in the opposite direction 180 degrees to the gradient. So I should move in this direction. This should be my u. So that is what gradient descent says. You should move in a direction which is opposite, or uh, yeah, in the opposite direction of your gradient. So this condition shows us that that condition should that I mean to say that situation, or let us say you want to move in the opposite direction of your gradient. So that is how we get this gradient descent algorithm.
Sorry to interrupt. So this theta is angle between. Uh,
No, theta is the set of parameters.
okay.
This beta is the angle between your current gradient that we have and what is the new direction that you want to take, such that your loss is minimized the maximum. So you can take one direction, it will minimize the losses. From 100 you can go to 60, from 100 you can go to 80, 100 you can go to 40. So obviously you will take this direction, right? Because it is the maximum decrease in your loss. So for going to the direction which gives your maximum decrease in the loss, you have to go in the direction of the opposite of the gradient, opposite to the gradient.
Okay, so we have to go means how that algorithm will decide that in what direction.
Yeah, so this Taylor series helps us to calculate in which direction can we go so that the loss in or a decrease in the loss is maximum. And if we calculate that, it comes out to be in the direction of the negative gradient.
Okay, and why we always use this cos beta, why not like sine or other
So
function?
this is, yeah, this is just for calculation. So if you just yeah, if you just derive it, you will just get back the gradient descent update rule that you have. So that is you had L theta plus eta u minus L theta, which was u transpose L theta, and you want this to be the most negative and it's -1. So you want this to be negative. So that means you want that uh, your, okay, how do I write this? Okay, let me check. So this calculation shows us that you have to move in the direction of the opposite gradient. So if you put u to be negative of grade of L theta, so that is what this Taylor series type of analysis tells you. If you put the new direction to be negative of this, you get your maximum or set of parameters that gives you the maximum loss, maximum decreasing loss. So that means you have theta t plus 1, you have theta t, and you have eta. So what is the direction you should go? You should go to negative of the gradient direction. So in general, you'll only use this. You don't need to go through all of these things. In general, you're only interested in this. This is just for showing that, okay, why do we need to go in the direction of negative gradient?
Okay, got it. Thank you.
Okay. Yeah, any more questions?
The delta value we will get from previous iteration, right? This delta, so that value will
This,
be set.
yes. So what was, so you will get some, yeah, you will get some loss function. So suppose your loss function is, so you have some simplicity y equal to ax square, and now your gradient of your loss function is 2x. Now you put in your previous value of the weights at x, and you get the this value at the previous iteration.
Okay, but for first iteration, that delta value will not be there, right? Because for first iteration, there
Oh,
won't be any graph.
no. For first iteration, anyway, you will say that my theta 0, which is the initial, you will say that it is some random number. So let us say it is say 1.5. And once you have theta naught equal to 1.5, you will calculate your loss. So what is my loss at theta naught? It will give you something. And now you calculate gradient of the loss at theta naught. And theta equal to theta naught, you will get some value here. And now when you're doing theta 1, so that is theta naught minus eta times this gradient that you get here. And then you continue, then you can, for the next iteration, you will have gradient of theta at theta equal to theta 1. And using that, you calculate theta 2. So that is how you will do that.
Okay. So Taylor series is for determining the direction.
Yeah,
And,
it is for, yeah, it shows us how you can calculate the best direction that you want to go to.
Yeah, but every time we calculate the derivative, how that is related to this direction that we calculate here?
Okay, so why do we need the derivative at all? So why we need the derivative is that because we saw that u can be anything. So what we are interested in is finding this direction u that you want to go to, right? So you have some, okay, once you have some function. Where do I go? You have some function here, and now you want to say which direction you want to go. You're free to go in this direction, you're free to go in this direction or this direction, and so on. But you want to find out what, so each of these is you says in which direction do you want to go. So once we use this Taylor series type of analysis and we see that we get the maximum decrease when we go in the direction of the negative gradient. When we set u equal to minus of this, that is when we get the maximum decrease. So that is why yeah, so this should have been theta t plus 1 equal to theta t minus eta u, but we don't know what is u. But because we want to get the maximum decrease in log, we say that okay, if we set u to be the negative of the gradient, so instead of this, if we send put negative of the gradient, then we get the maximum decrease. So that is why we use the negative gradient in this case. Is that clear?
Okay, but see, at every iteration we will be calculating the gradient, and the direction will be determined by this Taylor series. But in the
Yes.
final equation,
Hmm.
in the final equation, how we will represent the direction in the differential equation, final differential equation.
So final, so fi I'm
Final
not
means
sure what.
the equation at the end of one iteration.
Okay, after one iteration, you will get something like this, say, right? And now you'll calculate this gradient again because your theta is changing, right? Like earlier you had theta naught, now you have theta 1, next you have theta 2. So suppose you are calculating some theta, say 100. So theta 100 will depend on theta 99 and your gradient at theta 99. Because at each point, so you see at this point, your gradient was this. At this point your gradient is different. At this point your grade, so in this example it is same actually, but suppose you have some other figure, say something like this. So at this point your gradient was something like this. So at this point your gradient is something like this, or at this point your gradient is something like this. So at each point your gradient will be different. So at each point is grade of L at theta will be different. So that is why you need to keep on continuing. So it depends on how. So suppose you want to run say 1000 iterations. So you will at the last step your 1000 update will be something like this. Gradient dot theta 999. So that is, so I don't know if I'm clear about the question, but there is no final equation that you have. This is the type of iterative type of equation that you will keep on running to update the weights.
Okay. Yeah, but initially we calculate beta value, right? The angle value we have calculated.
Oh no, you
So
don't
are we
have to calculate
substituting it
this.
somewhere? We calculated somewhere beta value.
Oh, so this again, this was for just analyzing how you can get this. You don't have to calculate this beta
Okay,
or
internally
this.
we will calculate and substitute wherever
Uh,
required.
you don't have to worry about all of these things. These are
Okay,
just for proving that you want this.
understanding. Yes.
Uh,
We need to-
so only thing of interest is this equation.
Okay, got it.
Okay.
Thank you.
Okay. Yeah, any more questions?
So, so there are no questions related. Like I don't have any more questions related to the slides. But just asking on this tailored series, like if it, like I think this might be out of the context also. But just to understand, like what?
Yeah, can you repeat? I did not get.
Yeah, just to understand this tailored series, right? What it is, because when I'm seeing, I just read a short document on it. Like it's telling that if we have a point, it will
Yes.
tell what happens to this point after like certain number
Okay.
of operations we do. Is that the right understanding of the Taylor series?
So, so this is actually a function approximation type of thing. So suppose we all know that, let us say we have something, uh, we know what is the, suppose we have some function of this type. We know how this will look like. Or you have something like y equal to x cube. We have something like this. But now let us take a reverse direction. Let us say I give you a function something like this. Now we don't know what this function is. We want to find out what this function is, but we have no clear. Maybe this is easy. I don't know, but we don't actually know what is the clear formula for this function or how you can express this function. So one way to do or analyze this is, instead of looking over the whole, suppose this function is over this range, instead of looking over this whole, I mean to say the domain, or instead of saying what is the function between say -100 and +100, I'm just interested in what my function looks like locally. And locally I mean, so suppose at this point I fix a point, say x, and now what does my function looks like around x? So by around x I mean a neighborhood of x. So say in this portion, so this is x plus h, and this is say x minus h. What does my function looks like in this domain? So this is what Taylor series gives us. It does not tell us how the actual whole function looks like. It just says locally in around some neighborhood of the point, how does it look like?
Okay, so it gives the equation of this function. Okay, got it.
You can say, yeah, equation of this function. So suppose let us say this is my y, or not y, f, say. So I can write what is my neighbor. So I am at a point x, and what is my function in the neighborhood of x, say f of x plus h. And so this gives us something like, so the Taylor expansion is a defined, the series has already been defined. So it goes something like this. You have this and some h times gradient of f at x plus h square by 2 factorial times. So don't have to worry about this. gradient of fx, and so on. Then there are h cube terms, and then there are h4 terms, and so on. There are a lot of these terms. So what does this say? So I'm at a function f, so this is fx, right? This is fx, okay? Now this thing, so if you remember your geometry correctly, so we have this y equal to mx plus c type, right? So this is the equation of a line. So
Yes.
this is what we have. This is some h, and this is your m. This is your slope. So if we just consider these two parts, if we consider these two parts, so at this point you have some line type of, you say that my function is like a line,
Okay.
say. And now if I go one step higher, let us say I consider this point also. So
Okay.
you have like
Curving.
x h square and this. So now you have a parabolic type of approximation. So you say my function is something like this. And now if you go to higher and higher points, you will go something like this. And overall, the more number of terms that you go, the finally you will get back something like this.
Okay.
So
So
that is
basically,
why,
that line is becoming a curve as we are increasing, right?
yeah, if you increase the number of terms, you get more closer approximation to the actual function.
Okay.
How does the function look like?
So this can be done for any functions, right? There are no restrictions on the functions. Like,
Yes, yes, it is applicable for any function. Yes,
only thing it should be continuous. It cannot be a discrete.
yes, because these gradients, these should exist.
Yeah,
Uh,
gradient doesn't exist, but
yeah, should be differentiable and can continuous.
So, in continuation to this Taylor series, just
Yes.
in case if it is there in the scope, if it is not in the scope, it's fine. I had done a course in this Taylor series, Taylor expansion,
Mhm.
and towards the end, what I never understood was this big O notation.
Okay.
I
Huh.
was just not able to understand how are they doing. I tried doing some different videos and all, but never got to understand that,
Oh, okay.
how to approximate that.
Huh. So, yeah, are you aware of the big O notation in the way it is used in computer science?
No, I
Okay, so
just know
then,
it is used. That's all I know. I
huh, huh,
don't
huh.
know, but it was I did not understand like higher terms. How are they approximating and giving that big O notation?
Yeah, yeah, yes, sure.
It is used
So,
for fine tuning. Beyond that, I don't know.
so in computer science, and it is not related to this Taylor approximation. So
Hmm.
if we run about algorithms, and so you always say talk about how complex some algorithm is.
Hmm. Hmm.
So
Hmm.
complex mean whether it will take quadratic time, cubic time. That means if I have say 100 n number of points, and I want to
Hmm.
say, let us say, sort these n points. So there are some algorithm which will require n squared time. So I'm assuming each point takes say 1 second. So if I have say 10 points, it will take 100 seconds. So that is just an assumption, but that is how this big O notation goes. So if I say I have some sorting algorithm, say sort algorithm S, and I have some n number of points, and if I say that this is O of n square, that means
Hmm.
this algorithm will take me time which is proportional to O of n square. So that means, so suppose I plot the running times. So this is my n, and this is my running time, let us say. And so as n increases, my running time becomes like quadratic. This becomes a quadratic type of function. And big O means it can be at most this. So before that, suppose I have a quadratic function here. So I have some, this is my actual some quadratic function n square, and my
Hmm.
algorithm will take say half of n square or something like that. Suppose my example takes half of n square. My sorting algorithm takes running time like this. So
Hmm.
big O means it can be at most n square and not more than that.
Okay.
So same thing happens here, because all of these smaller terms are, so let us say my age is say 0.1, right? So my h
Hmm.
square is 0.01, h cube is 0.001, and so on. So
Hmm.
if you see, all of these terms are, so h cube is, it can be at most h square, right? 0.001 is at most h square and not more than that. So I can write that this is at most h square.
Sorry, I did
So,
not understand this
huh, so
last.
my h, yeah, h cube is
H
0.
and H square, H cube, that much I understood. Then,
So this h cube or h to the power 4 and so on, it
hmm,
cannot be greater than this, right? So if
yeah.
you take this curve,
But I can say it cannot be greater than H also, no?
yeah. So suppose I want to take two terms of approximation. So it depends on how much approximation I am doing. If I just say that I want only one term of approximation, I can ignore all of this part and say that this is my O of h square. This can be at most O of h square. Or if I am just taking this part, I can say that this term is almost a O of h. What is the maximum value that that part can take? So that is given by this O notation that we have.
Yeah, but then both will hold true only, even if I say at most, I mean, it's no, it's more
Hmm.
than it is less than H also
Hmm.
is true only if I, but for different functions, the answer was different.
So I, what do you mean the
Or if you
answer?
can give me some reference where you can get
Oh,
this.
so even I am
Bec-
not sure if there are reference. So
Okay,
yeah,
okay,
for
okay.
understanding this BIGO notation, you can go to any basic algorithm type of lectures, and within the
Hmm.
first 2 or 3 lectures, they will discuss these different notations you have. So there is
Okay.
BIGO, there is theta, there is omega, there are these type of notations.
Mhm.
So when I say BIGO, it is means what is the maximum that that thing can take, maximum time or maximum value that
Yeah,
thing can
like in
take.
this example only, always my question, doubt in all. I mean, I did a Coursera course
Mhm,
on advanced calculus, and it was
mhm.
primarily Taylor series, Taylor expansion.
Yes.
And one particular portion of that was they would find this big O also, and
Yeah.
that I would always go wrong because I don't know how, because for me it is like, okay, it is greater than h also. Why you
Mhm.
saying it is I mean it, why are you limit, where will you put that limit? It is, I can say
So,
it'll
uh-huh. So you're
from h
basically,
also or h square.
hiding away the parts. So I don't want to
Yeah,
look
so
beyond h
I
square.
which
Uh,
all should I mean, what should be the limit to hide?
so so it
Depends on
depends
the
if you are
function
take,
maybe.
uh, depends. So if I want a one level type of approximation, I don't want to look at anything less than h or h square. So I'll just say f of x
Mm.
plus h plus the rest. The rest is at most of h square,
Mm.
and I don't care what those values are. Or if I want to
Yeah,
look at say,
they used to say that the degree of yeah, up to x square something. So
Mhm.
some such thing used to be there. Some limit will be there. So based on that, I will.
It,
Uh,
uh, so as far as I'm aware,
okay,
it's just for hiding away these extra non-important
okay,
parts.
okay. Yeah, yeah. Thank you so much, sir.
Okay.
Can we drop off if we don't have any questions?
Yeah, I'll be available till 5. So if you have no questions, you may leave.
Yeah.
But yeah,
Thank
I'll
you
be
so much.
Thank you.